Okay, let's. All right. Let's hop back to Zoom. Let me continue this one time to see if there are any people. There is one. Let me let him in. All right, let's save. Calculus for today. Okay. Next. And let's share the content. Oh, before we do that. So there was a request to go to the homework. So let's go on the homework. Okay. And again, like as usual, I'll do the best I can to kind of like explain some of the backstory and some concepts as we go through the homework. Now, you know, I just know that when I finished the recording for section 3.1, I didn't feel good, but I was like, I mean, and I intended to kind of go back and redo it. If I need to, I will. But I think majority of people right now wanted to go through. Now, look, notice for section 3.1, we have 13 questions, so I feel like that's not too bad. We'll do the best we can until for the next like right at about 30 minutes, and then we'll use the remainder of class to make our way through as many of questions from section 3.2 as we can. So 3.1 is covering using the first derivative to find local extrema, right? So the first derivative tells us whether the original function is increasing or decreasing. So remember, the derivative is the slope of the tangent line, right? So a function is increasing, you know, as we trace it left to right, the graph goes up, right? So if the graph is going up, the slope of the tangent line is positive. A function is decreasing, so we trace it left to right, the graph goes down, right? So that means the slope of the tangent line is going to be negative, right? So when the first derivative is positive, that tells us the original function is increasing. When the first derivative is negative, that tells us the original function is decreasing. So if a function goes from increasing to decreasing, right, is that the top of a mountain or the bottom of a valley? If the function is going up, 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 and then it turns and now it's going down, 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 that's going to be a relative max, right? So that's where the function is going to go from, the first derivative is going to go from increasing to decreasing, positive to negative. And then the analogous, if the function goes from decreasing to increasing, that's the bottom of a valley, right? So that's going to be a relative min. So this section is all about using the first derivative to identify the peaks of the mountains and the bottom of the valleys, okay? So in this one, we're asked to graph the function. Actually, I'm going to skip this one because this is a review question from something from before. I'm going to go until I get to chapter 3. Here we go. So this one asks us to draw a graph to match the description given. It says g of x is a negative derivative from negative infinity to 4. So that means the function is decreasing from negative infinity to negative 4, and then is increasing from negative 4 to infinity. So I think we need to zoom out. Let's do one more. Okay. So one of these graphs is, we're looking for the one that's going from decreasing to increasing. So it has to be either B or C. Has a negative derivative. What's the difference? Draw a graph. Okay, let me see. Has a negative, oh, okay, negative 4, right? So that negative 4 refers to the x value. So the graph needs to be decreasing on the left side of negative 4 and increasing on the right side of negative 4. So it can't be A and D because those aren't behaving properly. But then it's not C because C is centered around, that looks like 1, 2, 3, 4, positive 4. But we need to be centered around negative 4, right? So this interval, this negative infinity and this to negative 4 and all of that, that's talking about the x-axis, right? So then this one should be B. Again, you just have to stop me. You have to unmute yourself if anything is not clear, right? We can talk about it. And again, the original intent of class time is to be a Q&A. Let's see. Draw a graph to match the description. It says f of x is a negative derivative from negative infinity to -1. So it's decreasing left of -1 and right of +3. But then it's increasing between -3 and 1. So it's going down, up, down. So down, up, down. It could be A, right? We're going to let that one be. It could be B. It can't be C. We said down, up, down, and it can't be D, right? And again, if anything isn't clear, just stop. So then it says what? Left of -1, right? It should be what? Decreasing, and right of 3. I think.
Hey, Professor, are you sharing your screen?
Oh, you can't see. Okay. Dang, that means we got to the other one. Starting the broadcast. Thanks for that. I was not sharing my screen. Well, we'll let the other one be for now. Okay, so it says draw a graph that matches the description given. It says it has a negative derivative between -infinity to -1. So it's going down to the left of -1 and to the right of 3. Okay, so it's I'm torn between A and B, right? Let's see this. It looks like -1, 1, 2, 3. This one is decreasing left of -1 and right of 3. Let's look at B. It has a positive derivative. Oh, but okay, here it is. But f prime of 3 does not exist. So when x is 3, so then because of the extra part, that was like, it could have been either of those. But then that last part that says that f prime of 3 does not exist, so we can't have the derivative, we can't have sharp corners for the derivative, right? So then the derivative does not exist when x is 3, so it should be this guy. Yeah, okay, let's go with that. I was like, I couldn't find the thing that distinguished them. Let's try another one. Okay. So here we're asked to find any critical values and any relative extrema. So the critical values are going to occur when your first derivative is either 0 or does not exist, right? So the derivative tells us the slope of the tangent line. If the slope of the tangent line is 0, that means that's a candidate for a relative extrema. Also, if the first derivative does not exist, that's also a candidate for a relative extrema, right? Let's take some notes. Let's take some notes. Let's zoom in just a little bit. I'll let that be for right now. Come on. There. Over here. So I need to move page. Let's cut this. And again, I need to do the title. I meant to paste it from earlier. Methods. No, under. So this is a homework session. This is 3.1 using first derivative. And 3.2 using second derivative. This is calculus in business. Spring 20. Okay, so find any critical values. So again, the critical values are going to occur when the first derivative is either 0 or does not exist, right? So given something like this, let's go ahead and find, again, if our original function, if our f of x, we have x squared plus 2x plus 4, let's go ahead and find f prime, the first derivative, right? So then the first term, the derivative of x squared is 2x. The derivative of 2x is 2, and the derivative of 4 is 0, right? So then the critical values are going to occur when the first derivative is 0 or does not exist. There aren't any x's that's going to make this where it does not exist. So what we're going to do is set f prime of x equal to 0 and solve. So then if we have 2x plus 2 equals 0, x equals -1. Right? Now we need to verify that this is a relative extrema, right? So we're saying that when x is -1, the slope of the tangent line should be 0. So that means, what that means is in our graph, we're either going to have, it should be the top of a mountain, the relative max, or the bottom of a valley, which is relative min, right? So we can use the first derivative test to verify whether it's one or the other. So for instance, we're going to let this be a positive x. We're considering when x is -1, and we want to evaluate it in f prime of x. When we put -1 into f prime of x, we get a result of 0. So now we want to test a number on the left and the right to see how f prime behaves. So for instance, a number to the left of -1 would be something like -2. If we put -2 into f prime, 2 times -2 is -4, plus 2 is -2, right? So the results over here, so f prime is negative in this region. So what that means is that our original function should be decreasing. So our original function should be decreasing on the left-hand side of -1. Let's test a number on the right-hand side of -1. So to the right, an easy number would be 0, right? If we plug 0 into the first derivative, we get 2, right, which is positive. So then the first derivative is positive on the right-hand side of -1. So that tells us that our original function should be increasing. All right. So then if you think about the graph of this, the original function, the highest exponent is a 2. That means it's a parabola. The y-intercept is 4. From college algebra, we can actually jump straight to the vertex of this, which is -b/2a. So then it should be when x is -1, and so we get the same thing, right? So, and we have that is the original graph is decreasing and then it's increasing. So that means that we have a relative min. This is a relative minimum value. Relative min. When x is -1, the corresponding y, 1 minus 2 is -1, is 3. Right? So that 3, I just got it from plugging into the original function. Okay. So we use the first derivative test to verify that when x is -1, that's a relative min. Now let's hop back to Pearson and answer the question being asked. So it says, find the critical values. Use commas to separate the critical value. It should be just -1, right? Either x equals, I'm gonna just put -1 for right now. Okay. And then select the correct choice, and then any relative extrema. So the critical value was x equals -1, and then we found through the first derivative test by testing a number on the left and the right, we saw that the first derivative went from negative to positive. So that means our original function went from decreasing to increasing, which means that we had a relative minimum, right? So I think it's B, right? The relative minimum point, we got negative, what do we get? -1,3. Okay. I know it's more than likely it's a little bit overwhelming, but with these concepts, if you just kind of keep working them and keep trying, I feel like they'll get better. Because it's not as bad as it seems. The relative min points, so we got this point and there are no relative max, right? That's what we got. Let's check that answer. Okay. And again, just stop me if we need to go back. Let's try another one. So again, the first derivative tells us whether the function is increasing or decreasing, and we can use it to identify the relative max and the relative min. So basically the relative max is the top of the mountain, relative min is the bottom of the valley. It says the graph of a derivative is shown on the right. Use the information in the graph to determine where f is increasing or decreasing, and the value of an extreme, right? So this graph we have on the right here is the graph of the derivative. So when the derivative is positive, that means our original function is increasing. When the derivative is negative, that means our original function is decreasing. So it looks like a critical value where it goes from positive to negative is when x is -2. So left of -2, the original function should be increasing. And then 2, when x is 2, we're going to have a relative, looks like a relative max. And then to the right of 2, the original function should be decreasing, right? So again, that graph was the graph of the derivative. So let's see. Where is the function increasing or decreasing? It's increasing left of -2 and decreasing right of -2. Okay. Okay, and decreasing right here. So the function is increasing. So left of -2 means negative infinity. I think it was -2. And then decreasing from -2 to infinity. Okay. Let's see, how do we do? Okay. So that one's a little bit trippy. Sometimes those are just interesting to me when they give you the graph of the derivative, and then you have to use the information from the derivative to get a sense of the original graph, right? And so the reason that we kind of structured, and I want to take this moment to pause to kind of give you a little bit of like foreshadowing or foresight. So the reason for the pace or the rhythm that we have in this course, and again, this is the last week where we're going to be going through 4 sections in 1 week, right? After this week, I think for the rest of the semester, I think it's only 2 sections a week, right? So 1 section a day. This is the last week that we need to do 2 in 1. But with this one, I wanted to pause because again, with this graph, they gave us the graph of the derivative. And then trying to work backwards to get a sense of the original is, to me, it's like you can't be in a calculus class and not talk about that, right? That's this concept called integration. So so far we've been looking at all derivatives, how to find a derivative, applications of the derivative, so on and so on. So then now, what if you start with the derivative and you want to actually get back to the original function? That's integration, and that's like the mark. That's a big jump, because you're going to be using that going forward in any other math class, right? So integration is the reverse of differentiation, but that's what's coming in chapter 4, right? And so I did this rhythm so that we can do the best we can to get through chapter 4. I feel like I would be doing you a disservice if we didn't at least talk about integration, right? Because we need to. That's like important. Let's see, max, right? So we said our original graph went from increasing to decreasing. So we had a relative max. There are no relative maxima. When x was -2, now we don't know. Okay, when x is -2, right? -2. Okay, let me check Zoom really quick to see if we got. Nope, I don't want to stop. I just want to see if we got any people in the waiting room. We do. Let me let the student in. And so, I don't want you to. I know my presentation might be one way or another, and I'm doing the best I can to make it as amicable. If you sit with the information, I would encourage you all to like work together and link up with tutors and like ask me questions. If you sit with it, you'll get it. It's not as bad as it may seem at first glance. I just don't want you to be like discouraged. I want you to kind of keep pushing, keep trying, work together, just get it done. All right. Okay, let's keep going. Right here. Okay. We answered that one. Oh, was that it? No, that was just question 3. minimum or minima? No, there were none. We didn't have any minima. Nice work. A possible graph, right? So we said the original graph goes from increasing, and then it peaks when x is -2, and then it's decreasing. So increasing to decreasing, it can be A. I think it can only be A, because that's the only one that goes from increasing to decreasing and turns when x is -2. Right? So let's go with A and check. Okay. So with this question, it says find any relative extrema of the function, list each extrema along with the x value at which it occurs, identify the intervals over which the function is increasing and over which it's decreasing, and then sketch the graph. Extrema. So if we're talking about extrema, we need to look at the first derivative. Let me see the time. This is going to have to be the last one from this section. So let me pull a copy. Man, we only made it through like a couple of questions. But I mean, we're only working in like a 30-minute window. So, you know, that's expected. Okay. Right. So now, it said, find any relative extrema, list each extrema along with the x value, identify the intervals over which it's increasing or which is decreasing. Okay. So we can start with, we have this f of x. I'm just getting a copy. We got this -16 plus 7x minus x squared. Now let's consider the derivative, f prime. The derivative of a constant is 0. The derivative of 7x is 7, so that's going to be 7. The derivative of -x squared is -2x. Okay. So then the extrema are going to occur when this derivative is either 0 or undefined. This one won't be undefined, but we can find x that make it 0. So we're going to set it equal to 0 and solve. When we do this, if you add the 2x, divide by 2, x equals 7 by 2. Right? So this is our critical value. So then what we want to do to determine whether this is like, you know, an extrema and whether the graph is increasing or decreasing, we're going to plot this x on the number line. Right? So right here, x is 7 by 2, and we're gonna look at it through the lens of the first derivative, f prime of x. Okay. So we see the first derivative there. Again, this x value produces a 0 in the first derivative. And here, let's color code this. Anybody got a favorite color? I'm gonna go green. All right. So this x value has a 0 in the first derivative. So then what we want to do, we want to see whether the function is increasing or decreasing on either side of this x value, right? So thank you. 7/2 is what? 3.5. So a number to the left of 7/2 is like when x is 0. So if we plug x equal to 0 into the first derivative, we get a positive result, right? If you plug any number to the left of this x into the first derivative, you should get a positive result. Okay. So then with the first derivative being positive on the left-hand side here, what that tells us is that the original function is increasing on the left-hand side of this x value. Let's choose something to the right. This is 3.5, so we can choose like 4 or 5. I'm going to choose 4. If we plug 4 into the first derivative, we get a negative result. 7 minus 8 is negative. So any number to the right of this should be negative, which tells us that the original function should be decreasing. So if the original function is going from increasing to decreasing, is this a relative max or is this a relative min? Are we at the top of a mountain or are we at the bottom of a valley, right? So this is relative max, right? So now based on the original, we have a relative max when x is 7/2, and the corresponding y, we need to find that by plugging it into the original. So I'm just going to use my calculator. I'll go to y equals, we got -16 plus 7x minus x squared. Okay, I'm going to quit. And I just want to call in that function that I just typed in. And when x is 7/2. Okay. So then the corresponding y, we got a -3.75. Right. So we should have a max at this value. Okay. Let's take this information and go back to Pearson and answer the question. Okay. This one. Thank you. So describe any relative extrema. Our claim is that we got a max, right? And we did not get a minimum because, again, if you think about this original, the highest exponent is a 2, right? That means we're working with a parabola. The leading coefficient is negative from that negative x squared. So that means we have a downward facing parabola and the y-intercept is -16, right? So the relative max, what do we get? Some type in order pair using integers or fractions. So we got, my dog is just pacing like, geez. I think this one, right? We got what, -7/2, and then comma 3.7. -3.7. Please, Malachi, go to bed. Lay down. Go to bed. Let's go to bed. -3.75. Negative. Okay. Let's give this a go. Okay, we got a max at this point, and there are no relative min. Let's check. Okay. Let's see. Okay, increasing. So at this point, we got that left of this x value was increasing. So it was increasing from what? -infinity. So we're going to do parentheses. It was increasing as x went from -infinity to, what was that? 7/2? And then decreasing from 7/2 to positive infinity. Let's see how to do that. And then we said it went from increasing to decreasing, so it can't be A and B because those are going from decreasing to increasing. And then 7/2 is like 3.5. So between C and D, it's going to be D because the peak is on the right x value. The peak on C is at the wrong x value. On 7.5, right? Positive 7.5. Okay. Let me see. So we'll let that be for section 3.1. I mean, obviously we have more questions. I'm going to try to use the remaining class time to work some questions from section 3.2. Can we just go back? Okay. Let's work 3.2. Right here. So 3.1 was over using the first derivative to find max and min. So now we're going to look at ways of using the second derivative to find max and min. So while I get to that first question, the second derivative, what it tells us is the concavity, which way the curve opens. So when the second derivative is positive, that means that the original graph is concave up. That means the curve opens up like a cup. When the second derivative is negative, that means the original graph is concave down. And so it's like having a dome, right? The hollow dome or whatever. The curve opens downward. So then with this one, we're asked to, we're on 3.2, so let's do 3.2. For the following function, give the coordinates of any critical points and classify them as relative max or min, or neither. Identify the intervals over which is a. So the question parts A and B are from 3.1. The C says give the coordinates of any points of inflection. So a point of inflection is where the original graph goes from concave up to concave down, or vice versa. And so the concavity comes from the second derivative. So then part C comes from section 3.2. Identify intervals over which the function is concave up or concave down. Again, that's based on the second derivative. And then put all this together. Okay. Let's get a copy of this and let's take some notes. So again, when I was a student at Morehouse, there was a sign that said, I was walking down the hall and there was a sign that said somewhere, it said, there's no such thing as what we consider to be complex is really, oh no. All right, so I know I'm talking a little bit fast, and this kind of is information overload, but that's just because it's an introduction. There's a learning curve. You just got to take some time, sit with it, and keep trying, keep hustling, and you will get it. As long as you keep trying, you will get it. All right. If you give up at some point, then that's how the cookie crumbles. Okay. So let's start with part A. Find the critical values, right? So let's see. So we have this. I'm just gonna get a copy. We got this Q. That's not a Q. We got this Q of x equals, now the denominator is x squared plus 81. The numerator is x, right? So let's go ahead and find Q prime, and Q double prime. So the first and second derivative. Q prime. Oh man. So with this one, we have to do the quotient rule. So that's low D high minus high D low over low low. So that's going to be the bottom, which is this. The derivative of the top is 1 minus the top times the derivative of the bottom is going to be what? Just 2x. And then all over the bottom squared, which is this guy. Now this second derivative is shaping up to be a pain. Let's see if we can kind of like simplify this down some. We got 2x squared. So 1x squared minus 2x squared is a negative x squared. So it looks like we have 81 minus x squared on top. And on bottom, we have x squared plus 81 squared. Right? Now that 81 minus x squared, that's the difference of squares. We can factor that, but because nothing's canceling, I'm just leaving it like this. And then we need to go ahead, let's go ahead and find the second derivative as well. So then Q double prime of x. Okay, so let's do the quotient rule again. So low D high minus high D low. So the bottom, which is this guy, hopefully this will be okay, times the derivative of the top, which is going to be what, a negative 2x, minus the top, I'm running out of space, I'll shrink it down momentarily. The top is this. So the bottom times the derivative of the top minus the top. Now the derivative of the bottom is going to be this 2 times x squared plus 81 times 2x. Because we had to use the chain rule, the derivative of the outside times the derivative of the inside. And then it will be all over the bottom squared again. So that's going to be x squared plus 81. Now it's going to be to the power of 4. Malachi, please, lay down. Lay down. Lay down. She's pacing, and it's just like, you don't realize how anxious that makes you until get down. Lay down. Okay. Go to bed. Come here. Come here. Come here. Lay down. Get down. I think she just wants some attention. You can't give her attention right now. Any more than I'm giving her. Okay. Like this, like this. And I'm gonna just get this on one line so it can look a little bit better. So that second, second derivative, sometimes they get like that. Like it just can be like too much. Okay. That's a little bit crooked or whatever. And they just don't want to cooperate. Okay, let's I mean it's fine. It's not a big deal. Just this guy, this argument. Right, it's so crooked. Anyway, okay, we're gonna go with that, right? We need to simplify this. Notice they both have the x squared plus 81, right? Let me highlight. So we have, that makes it 3? No, those don't combine. So we have an x squared plus 81 here, and we'll do that in blue. And we have another x squared plus 81 here. They both have that term. They both have a 2x. We can factor out a negative 2x from both of them. So like there's one here. I'll do that one in orange. And then the negative 2x on the right, it comes from here with this. So we can factor out a negative 2x from those. Okay, let's do this factor really quickly and see if we can simplify this down some. So we're factoring out a negative 2x from both of them. They also both have this x squared plus 81. Now, from that first part, what's left, there's an additional x squared plus 81 left over. The negative 2x has been addressed. Now that's going to be a plus 81 minus x squared persists. The blue and the orange is gone, so then there's a 2 right here that persists. And we need to close off the parentheses. Okay. So we brought a blue to the front, an orange to the front. And then on bottom, we still have this x squared plus 81 to the power of 4. Okay. So now we can get a cancellation. That was the whole point, right? We got this guy cancels one of these in terms of 3. And it looks like we can combine this in like terms. Okay, we're almost there. So we get this negative 2x. That's making it worse. And the extra 2 is throwing things off. I feel like I got this one wrong. Let me see. X squared minus 2x squared is going to be a negative x squared. So we have a negative square persisting there. Let me see. We got 81 plus 2 times 81 gives us 3 times 81, 243. Okay, so plus 243. I don't think that's a perfect square. Okay. And then the denominator, we got this x squared plus 81 cubed. Okay. Hopefully we didn't do too much extra. Yeah, those things can be a little intense, right? Okay, so critical points. So now the critical points come from the first derivative. So if we set the first derivative to 0, it comes from where the first derivative is either 0 or undefined. So a fraction is going to be 0 when the numerator is 0. If what? If x is 9 or negative 9. So the critical points are plus or minus 9. And then we have to find a corresponding y. And then I don't think there's any x that's going to make the denominator 0. Because if you set this to 0 and solve, this is a parabola that's been moved up 81 units. So it's entirely above this by itself is entirely above the x-axis. So the denominator won't be 0 in this case. But plus or minus 9 will make the top 0. So those are critical values. And then we just need to find the corresponding y. Let's hop back to Pearson. Submit. Oh, okay. So we got that plus or minus 9. Let's go ahead and finish this out. This might be it for me. This one trained me so well. Okay. So we got plus or minus 9, right? So let's, okay, right. So here's -9, here's +9, and we're gonna consider these in our first derivative, right? In our first derivative, these should have a value of 0, right? So this plus or minus 9 breaks the number line up to 3 sections. So we want to test a number, and basically, if you look at it like section A, section B, and section C, right? If we look in section A, we can pick something like -10. If we plug -10 into the first derivative, that's what? 81 minus 100 is negative. A negative divided by a positive is negative. So it looks like everything to the left of -9 should be negative in the first derivative. So that means the original function should be decreasing on the left of -9. Between -9 and 9, I'm going to choose 0 and plug that into the first derivative. If we plug 0 into the first derivative, this is going to be positive. This is going to be a positive. Positive divided by positive is positive. All right? So everything in here in the first derivative should be positive. This should be the case that our original function should be increasing between these two. To the right of 9, I'm going to choose 10. This is negative. This is positive. A negative divided by a positive is negative. It's similar to the argument we had earlier. And over here, negative in the first derivative. So our original should behave like this as far as increasing, decreasing, and constant. Okay. So now, so that means that -9, this should be what? A relative minimum value. And this should be a relative maximum value. Okay. And then we just need to find the corresponding y from the original. We're almost there. Like Smokey the Bear, wintertime, I need you to bear with me. That did not come out the way I wanted it. So let's ignore that. Okay. Let's see. We want the original y value, so we need the original function. All right. So let's go to y equals here. Let's do x divided by parentheses x squared. That's not an x squared plus 81. Okay. And again, trying to follow somebody else's work is a little intense. My suggestion is just do your best to get the concepts and the ideas from what I'm doing and then try it yourself. Because I even struggle trying to follow other people's work. It just gives me a headache. Usually what I do is I do it myself and then I compare, right? As best I can. Well, I mean, you know what I mean. So let's go to variables. At least I hope we do. Okay. So when x is -9, let's see. Let's hit math as a fraction. We get a -1/18. Okay. And then when x is +9, then we're going to hit math as a fraction. We get a positive 1/18. Okay. So we have our relative minimum value and a relative max. Okay. That was part relative max or relative min. Okay, we got part A. Identify the intervals. We've already identified the intervals of which the function is increasing or decreasing. Give the coordinates of any points of inflection. So for the points of inflection, we need the second derivative, right? And that's when this is either going to be 0 or undefined. Now, for it to be undefined, we would need a 0 in the denominator, but we're not going to get a 0 here. And then for the zeros in the numerator, we set each of these to 0 and solve. All right, so let's do that. I'm just going to kind of pull this off to the side. Let me copy. And I'm just going to work that here. I'm going to kind of just break it. So it's a new line. This is, I think this is part C. We want to paste. And we want to set each of these equal to 0 and solve. The battery's down. Let me see. We're almost done. We're almost done. This is going to be it. I'm just trying to switch my headphones. Okay, I'm assuming that you guys can hear me and everything is okay. Now, what we want to do is set each of these to 0. So if we set negative 2x equal to 0 and solve, we get x equal to 0. And then if we set negative x squared plus 243, if we set that equal to 0 and solve, so then x equals the square root . This one needs to do plus or minus, right? 243. Is the original function cubic? You got 3 zeros, so 3. Think about it. I see. Keep going with this. All right, so these are points of inflection. Let me think. We add and take the square root. We get this. 243. 6 and 3 is 9. That is divisible by 3. Let me simplify this down. Let's see. 8 times 3, so 81. 81 is what, 9 and 9. So ultimately, it's 3 to the power of 5. All right. So then 81. Nine times the square root of 3. Okay. So these are candidates for the points of inflection. So then, similar to the first derivative test, we need to take these values and test them against the second derivative, and then see how the concavity changes. Right. So let's do that. I think this is the it. 9 times the square root of 3. So we got 0. All right. This is the x-axis. We got our 0. This is going to be a negative 9 root 3. That's going to be a positive 9 root 3. Right. And we want to compare these in the second derivative. These should all give us zeros. And again, so these 3 key values break the number line up into 4 sections. Section A, B, C, and D. Okay. These should create zeros in the second derivative. So then negative square root of 3, let me see, 9 times the square root of 3. 9 times the square root of 3. That number is approximately like 15. So left would be like negative 20. So if we plug negative 20 into the second derivative, right there, let's see, negative 20. This is going to be, let's see, 400. So this is going to be negative. This is going to be negative. This is positive. This is positive. So it looks like ultimately all of that is negative, right? I'm just not showing it. This should be negative, which means that our graph should be concave down for region A. Let's keep going. We said that was like negative 15 point something. So let's choose for section B. Let's choose when x is negative 10 into the second derivative. And here. Now, if I had another calculator, it would actually, I mean, I'm pretty sure this one can find the derivatives for us. What I'm just going to trust that what we have is correct. And I'm gonna put this here. So on top, we got negative 2x. It's kind of short on time. Negative x squared plus 243. Okay. Then we're gonna say divided by x squared plus 81. Cubed to the power of 3. Okay, I think this is okay. So let's check that first one. Now, the first one we got a negative result, right? So let's see, for instance, if we go call on that function that we just put in, when we said we plugged in negative 20 and we got a negative result, okay? So you see the negative there. Between, in region B, we're gonna choose negative 10, right? So I'm just gonna use what I have. We get a positive result, right? So in region B, we got that the second derivative was positive, which means our original function is concave up. And then instead of negative 10, let's do positive 10. So for the second derivative, that means the original function is concave down. And then right, or in section D, we can do positive 20. So original is concave up. Okay, so we got our intervals. All right, so I think we're ready, and I think we can wrap this up. Now, if we put all this together, we might have to do a little bit of back and forth. Here, let's do it like this, so we can see. Part A, what are the coordinates of the relative extrema? Right here. So we got a max and a min. The minimum that we got was -9. It says use integers or fractions. So here, for the minimum, comma -1/18, -9. Is that the right one? By 18. Got 9, comma 1/18. Comma 1/18. Let me see. Okay. Intervals, is it increasing or decreasing? So you can kind of see it on the right hand side. Let's see. We got that it's increasing between -9 to 9. So -9 to 9. We got that it's decreasing. We got a couple of them. Simple type of answers. Use a comma to separate additional. We got that it's decreasing from -infinity up until -9. It's decreasing from 9 to infinity. Points of inflection. Okay. So the points of inflection occur where the graph goes from concave down to concave up or vice versa. It looks like we have 3 points of inflection. Let me think about this. It could be. Okay. We have the x's. We do need to find those corresponding y's. Let's see. Type in order pair, type in exact answer, use the radical as needed. Original. Okay, okay. To the original and find those corresponding y's. All right, let's just do that. Yeah. We want to paste. Okay. So now, for instance, cube of a negative 9 root 3. Okay. 9 times the square root of 3 squared plus 81. Square root of 3, right? Uh, 81 times 3 is 243. 3 plus 81 under 9 root 3. Is that 81? I think that's 81 times 81. $243 plus 81.
243 plus 81 is 324.
Okay, going. 324, right? If 9 by root 3, okay. I think you can divide both of those by 9. I think it goes back to 243. So this is going to be the square root of 3 over 243. The corresponding y. Let me see the other one. This is in tree. All right, I'm just going to take advantage of it. So when x is 0, the corresponding y is 0. Okay, I think we're there now. So now, if we go back here, no, we're about to wrap up. Points of inflection, right? So we got 1, 2, 3 points of inflection. Type in order pair, type in exact interest, radicals, use points separated right here. 1, we got negative 9 times the square root of 3. And then the corresponding y, we got the square root of 3 over 243. All right, hopefully we didn't mess up on our numbers. So we got 0, 0. 9 times the square root of 3, comma, be a negative, something like that. Square root, all right, square root of 3, thank you. For 243. Okay, we're gonna cross the fingers on this one. I was rushing trying to get to the end of it. Okay, we got these 3. Let's give it a go. That's what we can do. Let's see. I'm pretty sure we crunched some number wrong somewhere. Wait. I think did we plug it into the right thing? We can kind of check some of our work. All right. Let's do this. And I'm going to put the original in, which is this x divided by parentheses x squared plus 81. That I just typed in. Now we want to invite, first let's go ahead and test the 0. The output should be 0. That's fine. Now when x was at negative 9 root 3, so I'm going to call that on negative 9 times the square root of 3. Let's see, let's go to, get rid of that. And we got something like this, right? It should be negative. We got our negative. Okay. Hopefully that's all it is. Oh, okay, here, before we make that change, let's just confirm that what's the number we got, the square root of 3. And let's just go ahead and put that negative in there. We're gonna say divided by 243. Okay, it should be the same number. Oh, so we did make a mistake there. Okay, see, I was about to one of our checks. Let's crunch these numbers again, real quick. It shouldn't take that long. 3, 9 times 9 is 81. So 4. Okay, what's 324 divided by 9? That's where we went wrong. 324 divided by 9. It's 36. That's where. Okay. Trying to move fast and crush numbers now. That was a 36. So right here is a mistake. Let's make that change. Hopefully that was it. Let's see. So, and I think it should be a negative there. I feel better about this now. I'm gonna move to that. So this one, if this isn't it, then we just gonna lose this one because we're out of time. I think that I feel better about that. And then this one should be a positive. Adventure. Oh my goodness, that was an adventure, right? But so again, with these assignments, right? Because I get that they can get like kind of intense kind of fast. Let me see. Let's get this last part. On what intervals is it concave up or concave down? Okay, so it has to be C. Let me see, concave up. It is concave up on parts B and D. So let's do that really quickly. Parentheses, -9 times the square root of 3. And we gotta fix that parentheses. That's in the wrong spot. So until 0. And then it's also concave up from 9 times the square root of 3 to infinity. Down -9 times the square root of 3. From 0 to 9 to 9, comma. Times the square root of 3. Okay. Oh, all right. Sigh of relief. Right? Oh, come on. Okay, let's put all this together, right? Let's see, the first part, so the 9s were a point in question. Let me see the original. Okay. Decreasing to increasing to decreasing, decreasing, increasing, decreasing. It can be D, right? Because we said the original function goes decreasing, increasing, decreasing. So that cuts it in half. Then the points of concavity, we need 3 points of concavity. See, I think B only has 1 point of concavity where the concavity changes. So I think it's A. Let's just go with A. We're gonna that. Okay, if you're okay, let me go ahead and share a copy of this. Send it to Box. Not the notes. This is a homework session. Spring calculus. Okay. All right. So yeah, again, my recommendation, you just have to take your time. Again, everything is there. You just take your time. Definitely want to sit down with your classmates and sit down with the tutors and ask me questions, right? And just, just take your time and do your best. You have a little bit of like a little bit of a cushion. I just don't want you to get lax in the sense that you get unlimited attempts on these assignments. There's practically no late penalty, like 10%, you know, there's way worse late penalties that could be invoked or whatever. And, you know, I just want to encourage you guys to just keep trying. I'm not trying to go hard because this stuff is kind of a little bit intense. So it's like, okay, let me just try to be a little bit more gentle and like, you know, dial some of the stuff back, but we still need to get through what we need to get through, right? So if there aren't any burning questions, we're going to end the session here. And from one beautiful mind to another, enjoy the rest of your day, guys. All right, take care. I'll see you again on Wednesday. Peace.